So in this series, I want to talk about the technology which underlies Super.AI. What I want to do is dive into the secret sauce in detail. And so what we'll do is we'll start with a why. Why did we even decide to build this? Why are we working so hard on this? Then we'll go into the what. So this is involving the AI compiler and data programming. And then we'll have a few videos into the how. So let's jump into it. So AI is changing the world, as you know. I'm just going to go through some quick background material so we're on the same page, but don't take this as I don't think you know this. So this could have only happened now because it's built on these previous world-changing technologies. So for example, we can only get machine learning AI to work because we have a massive amount of compute. And we also can only get it to work because we have a massive amount of data because of the internet and information has been continuously digitized. And so just like when electricity came out, it had its killer applications, electric lighting and the telegram. AI had its killer applications, namely speech recognition, machine translation. But when, for example, electricity started changing the world is when it became ubiquitous. And AI is starting to become ubiquitous. It's now touching on point of society. And in fact, the biggest and most powerful companies in the world are AI companies. And these are the Googles, the Microsoft, Facebook, Apple. And they're investing billions of dollars building these AI algorithms. And we live in such a cool, crazy world that they typically open source these. And so with the advent of AI comes a new software paradigm, programming paradigm, which we call Software 2.0. I think this was coined by Andrej Karpathy. So we call traditional software, where you have a software engineer programming fixed rules, if-then statements, for loops in their IDE. And now we have a new programming paradigm, Software 2.0. And so we'll just give a concrete example of how this manifests in, for example, email understanding. So if I wanted to understand that someone wrote to me about their missing luggage, how would I do this in traditional software, aka Software 1.0? Well, I would need to come up with a set of fixed rules based on the syntax of my language. So if I wanted to understand that there was missing luggage and I needed to know the details of this, well, then I would need to start by saying, okay, is this class of email even missing luggage class, the missing luggage class? So maybe I would do string matching and write a regular expression to understand words like lost, missing, can't find. And then I would want to know details about that. So then I'd write other regular expressions. And so I'd maybe search for dates or search for flight numbers. And I'd have to do this in a massive number of ways because free-form, unstructured data can be very messy, as you know. And so this is a huge headache and a big reason why people don't do this outside of the most trivial cases. So whereas in Software 1.0, if it's a missing luggage intent, it's implied by the large amount of rigid rules. In Software 2.0, we say this is missing luggage intent if the neural network says so. So instead of a programmer programming it with fixed rules, the program is implied by labeled data. So instead of programmers programming, you have data labelers programming in Software 2.0. And so, like I mentioned, the program is implied by the labeled data, and you get this trade-off of massive amount of flexibility and a massive amount of power, but you trade off compute and data. So you need a lot of data, a lot of labeled data to make this work. And so this is essentially the difference, as you know, between Software 1.0 and Software 2.0. And so the interesting thing is, just like if you had bad software engineers, you'd have bad software. And most likely if you have really good software engineers, you're going to have good software. The same is true in software 2.0 because labeled data is the way you program software 2.0, as we talked about and as you know. And so if you have bad labeled data, then most likely you're going to have a bad machine learning model. And if you have good labeled data, then most likely you're going to have a good machine learning model. And so this is the key in software 2.0. And people are starting to realize this. So, for example, the head of AI at Tesla made this post about the time he spent during his PhD was mostly about algorithms, and while he's head of AI at Tesla, it's about labeled data. And Richard Zocher, the head of AI at Salesforce, said, rather than spending a month figuring out an unsupervised machine learning problem, just label some data for a week and train a classifier. And I've had this experience a lot personally. And Francois Collet, who is the creator of Keras and is at AI at Google, says if you're going to start a ML services startup, make it about data collection and labeling. This is a main pain point where the most value can be unlocked. He did a big survey on Twitter, and in fact, you see companies such as Google and Facebook. Google releases TensorFlow, open sources it in fact, but the interesting thing is they don't open source Endor, their data labeling platform, and same with Facebook with SRT, because this is so valuable, and it's so valuable in fact that they need to go outside to label data because they can't satisfy their own need. And so why is this the case? Well, the thing is, data labeling is fundamentally hard. It's not only hard logistically, but philosophically. And why is that? Well, the first thing is that quality is subjective. So if I show you this picture, well, if I wanted to put a bounding box around this, would you say this is one car, two cars, three cars? Well, for a surveying example, maybe I'd put a bounding box over each car because I just want to see what's on the road. Well, maybe if I'm Tesla, I want this to be one car because this is moving as one rigid body, and I want to treat that as one car. So this is subjective. For example, is this a bike or a car? Well, again, it depends on your application. Do I want to label obfuscated cars? This is a little more in the weeds. Or do I just want to label cars who are directly in front of me? And what speed is this? Do I call this 60 or 80? Well, it depends on the context. And maybe I want to create a new, more complex data type. Well, these are all subjective and dependent on what you actually want. The other interesting thing, as you know, about machine learning, software 2.0, is that the edge cases are typically the normal cases. So instead of programming deterministic fixed rules, we're learning statistics. And so the interesting thing about the real world is that most data follows somewhat of a regular distribution. So most driving data looks like this. But the times I really want to get it right are when I'm driving in the snow or there's debris on the road or construction. And this data is relatively rare, or you want to understand exceptions in your chatbot data or important things in your documents or emails, and those are typically the edge cases. And so the interesting thing is, because it's learning from statistical distributions, machine learning does really good in the fat parts of the distribution, but it doesn't on the tails of the distribution. But those are the ones you want to get right, and so it becomes really important to get very good labeled data on the tails of the distribution. And then finally, it's really important that this is an iterative process. So the problem with machine learning is if you label data and you just have this fixed asset of labeled data, if anything changes in the world, if your subjective wants change, then you have to throw out all the data. So this tends to be a huge bottleneck in the real world. And so the reason these problems come about, this is our hypothesis, that there's no programming stack yet for software 2.0. So let's go 50 years ago when people were first using computers, CPUs. Well, only the smartest people in the world could harness the power of computers, because they not only had to understand the hardware, they had to program it in binary, which is extremely difficult, unintuitive for humans. And so the market for computers was small. And then people started building abstractions on top of machine language. So they built an assembly language, which was more human readable, but still difficult. Then they created a compiler, APIs, and now almost anyone can use a computer because we have graphical user interfaces. So you just move your mouse, click, and you can harness the power of computers. Well, what we see as an analogy is software 2.0 is kind of where software 1.0 was 50 years ago. And so essentially what we're doing is we're in this machine language where, just like computers only understand binary language, well, AI only understands labeled data. And the way people currently do it is they just label the data, just like you would directly program a computer with binary. And so, as an analogy, only the most powerful, biggest companies can really get AI to work in the real world because it's so complicated to program it on this machine language level. Does that make sense? And so what we did at Super.AI is we built a software 2.0 development stack. And so what it does is we built abstractions on top of data labeling so that you could get the same benefits as you got in the software 1.0 abstractions, and you can harness those in software 2.0 abstractions. And so what we did is we built the analogy of an assembly language. We call them labeling primitives. We built a compiler, which we call the Super.AI compiler, and it's analogous to the software compiler. We took a lot of inspiration from the software compiler. And so you can, and then we invented something we call data programming, which is essentially equivalent to C programming language, but it allows you to manipulate the labeling primitives in a Turing complete way. And so you get all the benefits of software: modularity, abstraction, reusability, auditability, but you can still use that to program software 2.0 applications, which are inherently statistical. So we believe this is the best of both worlds, and so we call this the software 2.0 development stack. And the key innovations are around data programming and the AI compiler. Okay, so we're going to go into the details of the AI compiler and data programming, but I just wanted to cast this in one more way to drive home the point. So how do people today program in software 2.0, aka train a machine learning model? Well, they label data, typically randomly. If you're really advanced, then you would use active learning. Then you kind of pray that the optimization algorithm generalizes to your test set and ultimately your production set. And if it doesn't, based on customer feedback, or you see prior distribution or covariate shift, then you label more data, and you do this over and over again. And this is really expensive, which is why only the Googles and the most well-funded companies in the world can get this to work. And so compared to what it could be, this is very low quality, very slow, frustrating, and static. You have this fixed commodity of labeled data, and if you need to change anything about it, you need to relabel it again. And so you're creating a multiplier on the amount of cost, the amount of time, and ultimately the amount of frustration. And so the new way to do this, which we believe is the best, is to not do that and simply decompose your software 2.0 application, or what you ultimately want to do, into a reusable program. And so then behind the scenes, the AI compiler finds and labels only the most valuable data. It routes to the most optimal labelers, whether they're human or machine, and we'll get into this. It can guarantee quality. So as you know, because of the statistical and probabilistic nature of machine learning, it's really hard to give quality guarantees. But if you move back into the deterministic nature, at least for a piece of that, then you can actually have strong abstractions and guaranteed SLAs. The other thing is the AI compiler makes this improve over time, and you can update labels incrementally. And so you no longer have this fixed asset because you have a program which is dynamic. And we say this is the fastest and most efficient way to train AI, and this has been our experience. And so what it does is it takes you from this old way where this is where we've seen over and over again, and you've probably read these as well, why 90% of enterprise AI projects fail, into this new way of decomposing this into a reusable program. Great, so I hope you got at least a reasonable overview of the why. In the next few videos, we're going to go into the what and the how. And in particular, in the next video, we're going to dive into the secret sauce and talk about data programming. So I'll see you in the next video.